Hi, it's me, Dr. Prasad Puthiyillam. Continuing my classes on superconductivity, class number 5. In previous class, I explained about the basics of low temperature superconductivity, Meissner effect, type 1 and type 2 superconductors, features of superconductors. This class will explain about isotope effect as well as high TC or high critical temperature materials. Isotope effect. In 1950, Maxwell and Reynolds they introduced or they found that when certain isotopes or isotopes of mercury, when they work on the critical temperature of isotopes of mercury, they found that, so I'm drawing the graph of TC versus the atomic mass AMU of mercury. They found that the atomic mass 119.5 AMU of mercury, its critical temperature is found to be 4.185. And for the atomic mass unit of 203.4, the isotope of mercury, it showed the critical temperature of 4.146. That means if you observe, it follows a trend. So we can say, according to isotopic effect, the critical temperature Tc of superconductors varies with isotopic mass or isotope mass m according to the following relation. Tc is directly proportional to 1 by or 1 upon m to the power alpha, or Tc m to the power alpha is a constant in which the alpha is a number called isotope coefficient. The alpha values of mercury is 0.5 and for zinc it is 0.3. High critical temperature materials. The label high critical temperature material or high temperature superconductors or HTS, it should be reserved for the materials with the critical temperatures greater than the boiling point of liquid nitrogen. The liquid nitrogen boiling point is 77 Kelvin or negative 196.2 degrees Celsius or negative 321.1 degree Fahrenheit. So there are a few exceptional cases also. The majority of high temperature superconductors are ceramic materials, so they are type 2 conductors. The major advantages of high temperature ceramic superconductors is that they can be cooled by using liquid nitrogen. On the other hand, the metallic superconductors usually require a difficult coolant, mostly the liquid helium. The main class of high temperature superconductors are in the class of copper oxides, some particular copper oxides only. The second class of high temperature superconductors for practical applications are the class of iron based compounds. Many ceramic superconductors physically behave as superconductors of type 2 or second type. High TC materials are type 2 superconductors which allow magnetic field to penetrate their interior in quantized units of flux or in quantums, meaning that much higher magnetic fields are required to suppress the superconductivity. Example for high temperature supermaterials are cuprate superconductors, in which the superconducting property it is determined by the electrons moving within the weakly coupled copper oxide layer, the UO2 layer. Examples are yttrium, barium, copper oxide, and bismuth, strontium, calcium, copper oxide. A second class of high temperature materials are iron-based superconductors. Iron-based superconductors contains layers of iron and nitrogen, that is nitrogen family such as arsenic or phosphorus or a chalcogen. Examples are LaFePO, that is lanthanum iron phosphorus oxide, it shows superconductivity at 4 Kelvin, and LaFeAs oxide or fluoride will superconduct at 43 Kelvin. The highest temperature, critical temperature superconductor based on iron family, iron-based superconductors are FeSc, thin films of FeSc. Its critical temperature is above 100 Kelvin. The barium or potassium iron arsenide are later materials with pair of iron oxide layers. They are having a TC value up to 38 Kelvin. Preparation of ITC materials or superconducting materials. The simplest method for preparing ceramic superconductors is solid state thermochemical reaction, which involves mixing, calcination and sintering. There are even solution chemistry process, solution techniques such as co-precipitation, freeze drying, sol gel methods or alternative methods. The appropriate amount of precursor powders are mixed thoroughly using a ball mill, which is then calcinated in the temperature ranges from 800 degrees Celsius to 950 degrees Celsius for several hours, which then cooled, reground, calcined, and the process is repeated several times in order to achieve a homogeneous material. And these powders are subsequently compacted to pellets and sintered. So that's about isotope effect and high temperature superconducting materials. So this class ends here for superconducting class series. Thank you very much for watching and have a nice day.